Shruti, and as you can see, it's supersymmetry, big supersymmetry.
Great. Okay, so can you hear me? Through the mic, right? Okay. No? It's on, yeah. You can increase the volume, maybe? Oh, okay. I guess to say words until you can hear me. Can you hear me better now? Great. Okay, so today we're going to talk about supersymmetry. You might have noticed that a sort of subtle undercurrent in both Yaroslav's lecture today and also Lance's lecture, less subtle in Lance's lecture yesterday, was that special things happen when you have supersymmetry and you're dealing with supersymmetric theories, and quite often the best examples of the methods that we have been learning so far are in supersymmetric theories, right? And the favorite toy model of every amplitudologist is n equals 4 super Yang-Mills. Okay? We saw an example yesterday of how all plus helicity amplitudes, they vanish, all but one plus helicity amplitudes also vanish, and I said that this was a consequence of supersymmetry. So today, I want to go through how you figure that out on shell. How do you see the effects of supersymmetry on shell, right? Before we do that, though, I want to do a quick introduction to supersymmetry. I apologize if you've already seen this before, but I thought it would be good if we all start on the same footing. Okay? So supersymmetry, or the SUSY algebra, is an extension of Poincare, where you've introduced two new operators, Q and Q dagger. Sigma new. Okay. So these carry spinor indices A and A dot, similar to the spinor indices that we're familiar with from spinor helicity. In addition, these are Grassmann, so they anti-commute with themselves. Right? They also commute with momentum. And with spin, they act interestingly, which is to say that they act either, they act either as a raising or a lowering operator, depending on whether you're talking about Q or Q dagger, and whether you're massive, massless, etc. Okay. So good. So this is the extension of Poincare, right? And this is sort of the only non-trivial extension of Poincare that you can do as per Coleman-Mandula theorem, right? Okay, so what is the easiest example? The easiest example is always a free theory. So what if you're looking at just a Lagrangian, which is a free fermion plus a free scalar. Okay. Now, okay. So this Lagrangian has SUSY built into it, where I can define the transformation of a scalar like this, and for psi, B dot. Okay. Now, when you look at the right side of these transformations, it should be obvious that that was sort of the only thing you could have, right? So I should mention that epsilon and epsilon dagger, they are the SUSY parameters, right? So, for example, when you say that momentum is acting on a scalar field phi, then you say that this is how it acts, where A is the momentum parameter, right? The translation parameter. So epsilon is the SUSY parameter, epsilon dagger, similarly for for the other, for Q dagger. Good. So when you look on this side, this is kind of all you could have had for SUSY to mix bosons and fermions, right? And here as well, this is sort of the only thing you could have had. Good. I should have probably started by saying supersymmetry is a symmetry that mixes bosons and fermions. And that's kind of obvious from this, because if you lower or raise your spin by a half, you're going to go between bosons and fermions, right? Good, okay. So the first thing when I make this claim that you should wonder about is whether these transformations, whether they satisfy the SUSY algebra. And it turns out that they only satisfy the SUSY algebra on the equations of motion, right? So on the support of the equations of motion, meaning on shell, is when this algebra closes. Okay? If I want to close it off shell, I necessarily have to introduce other degrees of freedom, often called auxiliary fields. Okay? Good. So basically, you have two choices. The first is to use auxiliary fields and the second is to go on shell and see what you can get out of being on shell. Now, there will necessarily be things that you can't access about supersymmetry on shell, but today's lecture is just going to be about what we can actually do on shell. Okay. So what does this transformation look like on shell? Well, on shell, what we're looking at is some one-particle states, right? So you can think of the one-particle scalar state with momentum p, right? So these are all the states. It's the phi bar, psi with plus helicity, psi with minus helicity. Yeah, these are the states. So now you can define how Q acts on these states. So you can say that Q, let's look at the action of Q and not Q dagger. And you can analogously define the action of Q dagger as well. Now, clearly, there has to be something on the right-hand side that carries the spinor index, right? So the only object available to you is the square bracket P, okay? So, yeah, just to be clear, when I write square bracket, I mean lambda tilde P and angle bracket lambda P. Okay. And also clearly so Q actually reduces the spin of this state. And so what you get over here is psi minus. Psi minus spin can't be reduced any further. There's nothing in the spectrum, right? Additionally, Q is Grassmann, so you can't act Q twice on this state. So you get 0. Now, sorry, I thought I was acting on psi minus. This is 0. Good. Right, good. Now, additionally, you can do the same thing, and this gives you this. Yeah, and I think I mixed these up. Yeah. Okay. Yeah. They're all A's. All right, we can call this A dot if that's more usual or convention. Yeah, that's fine. Okay, good. I may have continued to make this mistake, so please continue to point out when I do. Good. Okay. So fine. So this is a particular example. This is what is called the n equals 1 chiral or scalar multiplet. You can already see the general structure here, which is you start with some state. You start with some state S. You act Q on it, right? And then you get QS, which is barring some factor of lambda, S minus a half, right? And then acting with Q again, you get 0, A dot. okay? Now, you might ask why I'm counting QA dot as one operator, right? Because actually A dot runs over 1 and 2. So technically, I should be able to write Q1, Q2, or 1 dot, 2 dot, if you will. But this need not be 0, right? And this is actually something special that happens when you are massless. And let's look at why. So when you're massless, you can always choose P mu equals, you can always go to a frame where this is true, right? Which means that your SUSY algebra now looks like this. P mu, which is 0, 0, 0, E. Okay, so clearly what this means is that any state that is generated with Q1 is going to be non-normalizable. Do you see why that's true? It's basically because if you have some state lambda, and you consider this state, the norm of this state would be this, which would vanish based on this anti-commutation relation, right? And yeah, as a result, you get non-normalizable states if you act with Q1. Okay? So all this to say that when you are in massless supersymmetry, the only object you have is one Q operator if you have only one amount of supersymmetry, so n equals 1. Okay? Good. So keeping this in mind, this is basically the structure of all n equals 1 multiplets, right? You have one top component, and then you reduce the spin by a half. Depending on your convention, you would call either S minus a half or S your Clifford vacuum, because it's annihilated by one of the supercharges. Okay. Good. So with this in mind, I'll just give you an example, which is n equals 1 gravity. Now, to get an n equals 1 graviton multiplet, I have two choices, right? The spin 2 can either be the S minus a half, or it can be the S, right? Which means I have two multiplets possible. One of them has 2 acting on it with Q will give you 3/2. So this is plus, plus, and then 3/2 when acted on with Q gives you 0. And then the opposite for the minus helicities. So minus 2 act with Q gives you 0, and minus 3/2 acted on with Q will give you minus 2. Okay? This is how the states work. This is one possibility. The other possibility is where the spin 2 is the lower spin, and the top spin is 5/2. So this is how you construct multiplets on shell. Okay? This is how you figure out what is the particle content of the theory that you're dealing with, the states. Good. Now, I think, so n equals 1 is good, but what is better than one amount of supersymmetry? More amounts of supersymmetry. So importantly, you can extend this supersymmetry. So what do I mean by this? It means basically that I'm going to take this algebra over here, and instead of having only one type of supercharge Q and Q dagger, I'm going to add an index to it, right? So I'm going to say that rather than just having one QA dot, I'm going to have an index on it, like this, okay? So it's going to be Q1, Q2, Q3, as many as you want to add, or as many as supported by the dimension that you're in. Okay, so this index is often called an R index, and so obviously adding this index is not going to change your first commutation relation. So it's going to be the same. Except now with a delta AB. Okay. What it can do, though, when you have extended supersymmetry, is you could possibly have a central extension of your algebra. So you could have something like this: AB, C, delta epsilon, AB. Okay. So you could have something like this, right? When you are, though, in a massless theory, you are subject, well, in any theory, actually, you're subject to the BPS bound that says that this central extension or central charge Z has to satisfy M greater than equal to the modulus of Z. Okay? So clearly, when you're in a massless theory, M equals 0, and so Z necessarily has to be 0. So what does this mean? No central extension. So as a result, we can really treat this extended SUSY algebra as just having more Qs available to us when we're building our spectrum. Okay? So what I mean by this, if I started with S, I can now act on it with QA. And that'll give me S minus a half. Act again with QB, gives you S minus 1, etc., etc. And you can do this as long as A and B don't equal one another. Right? Good. So now we're in a position that we can actually write down the spectrum of n equals 4 super Young-Mills. Okay? So for n equals 4 super Young-Mills, and you already saw this in Lance's lecture yesterday. What is the spectrum? You start with a gluon. So you start with a positive helicity gluon. You act on it with QA. Right? That gives you so a spin half. Let's call it lambda. Lambda now carries one of these indices, A. Act on it again with QB. Gives you phi AB, lambda ABC, and then again, we'll give you G minus. Okay. So these capital Roman indices are often referred to as R indices, and this is because, well, okay, so they're referred to as R indices. And you'll notice that these R indices actually transform, well, in the algebra, they're allowed to transform under something called an R symmetry, right? So in order to just preserve this commutation relation, I'm allowed to do a rotation in my supercharges, right, in the space of supercharges, as long as it's not messing with any of the other commutation relations that I have, right? So there is a symmetry group, so R symmetry group. And basically, this group only acts on the supercharges. It doesn't act on anything else. Right? Doesn't act on P, doesn't Q, nothing. I'm sorry, M, nothing else, just Q. Okay. So what is the maximal R symmetry group? Just looking at the algebra that you can have is UN, right? Where N is the number of supersymmetries. So number of SUSY is N, and then I can have a maximal R symmetry group, which is UN. Okay, so which is not, of course, to say that the interactions in the theory I'm building will preserve all of the R symmetry. It's just saying from an algebra point of view, this is a possible R symmetry group. So let me actually just look at SUN for the time being. Okay, so for super Young-Mills, this would be SU4, R, and this, so because this is a valid extension of the algebra, all of these states must be representations of SU4R, right? And it's very easy to read off what these representations are because QA is just that capital A is just a fundamental index in SU4R, right? So if, for example, so if you're familiar with Young Tableau, for example, you can just write G plus as dot, lambda A is box, phi AB is 2 boxes, lambda ABC is 3, and G minus is 4. And also, if you're familiar with Young Tableau, then you can see that this is actually just dot, this is box bar, this remains double box. Okay? So, yeah. So if this doesn't make sense to you, that's fine. You just need to remember that lambda has 1 R index. This has 2 antisymmetric indices, so it's a tensor. It's a 2-index tensor, antisymmetric tensor. Similarly, 3-index fully antisymmetric tensor, etc. Okay? Good. So now actually it's very easy to do this for other theories, right? So if I wanted to do n equals 8 supergravity, I can quite easily do this as well, right? So I start with H, I turn it with Q, I get, give me a Greek letter, so psi A plus, and you can keep doing this, right? So you get a photon, graviphoton, fermion, scalar. It's also very easy to count the number of these. Well, of course, if you know Young Tableau, then you can just calculate the dimension of these representations. But even otherwise, you can see that there's 4 of these. This is an antisymmetric 2 tensor, so 4 times 3 over 2, or 4 choose 2. This is 4 choose 3, 4 choose 4. Similarly, over here, 8 choose 1, 8 choose 2, 8 choose 3, 8 choose 4. Okay? So, so this that I've written down over here for supergravity is just half of the multiplet. Then you can continue like this with adding more and more supersymmetries, and that'll get you back to H minus. So these are what are called self-conjugate multiplets. You could have a situation, for example, if I was just doing n equals 4, right? Then this would become 4 choose 1, 4 choose 2, 4 choose 3, and 4 choose 4. And for any physical theory, you would also have the CPT conjugate of this multiplet, right? So that would have H minus now at the bottom, that's right, and then you would go up to the gravitino, the graviphoton, the fermion, and then the scalar, right, in the opposite direction. Good. Okay. All right. So before, I said that actually you could have a UN group and not necessarily an SUN group, right? Basically, what this means is that you can sometimes, depending on the theory, add a U1R extension of your R symmetry group. Okay. Yeah. So, yeah. Maybe in the interest of time, I'll just say that. Okay. That you should be able to prove that you can't actually give this multiplet or even that multiplet a U1R extension. Okay. And you should remember that what I mean by U1R is that each of these Qs now carry an additive U1 charge, okay? Which means that, let's say this has charge Q, this has R charge Q, this has R charge R, so this would be Q plus R, Q plus 2R, etc. Okay? But you should remember that gravitons have self-interactions. Okay? So, yeah, just I'll leave you with that. And you can decide whether you can actually have a U1R extension over here or not. And you basically will have to use the fact that gravitons have self-interactions. Okay? So, and yeah, and that these are self-conjugate multiplets. Good. Okay. So, any questions about how to build? Yeah.
So for the n equals 4 cryptography, how do you incorporate the negative multiplet?
Good. So I can't get the helicity states from here. So this is one multiplet all on its own. Now, independently, I have the CPT conjugate of that multiplet, which then will look like H minus psi gamma, what did I call it? Lambda psi. So just the opposite of the multiplet, basically, now with negative helicities. Yeah, that's right. Which is necessitated, as I said, by the fact that you have to have a CPT conjugate. Yeah. So if you have H plus, you have to have H minus. If you have H minus, you have to have this tower, because supersymmetry. Yeah. Yeah.
You mentioned this BPS bound.
Mm-hmm.
Where does it come from?
It's actually just a self-consistency condition on the algebra. So what I did over there with choosing that particular frame for P, so instead of doing that, you choose a massive frame where you have M000. I mean, you can always, a rest frame for a massive object, and then you can show that just that, like all of those commutation relations will lead you to this particular bound having to be true as long as all of your states are normalizable. Yeah. Yeah. So you do need to. Yeah. This bound comes from needing that your states have good norms, positive norms.
And the mass is which mass from the scalars or the fermions? Or?
They all have the same mass. I should have said that. All of these states have to have the same mass because of supersymmetry. That is also part of the consistency conditions that the algebra enforces. Yeah. So everything has to have the same mass, which is why all of these also are massless. Yeah. And which is why this is not telling you that some particular state has it. The whole multiplet has this mass. The whole multiplet has this charge. And then it has to satisfy this BPS bound, which, which, as I said, comes from consistency conditions on just the algebra. Okay. Okay, good. So now that we've talked about spectra, the next and most important thing that we're all here for is talking about amplitudes. Okay, so in general, sorry, 1 second. Yeah, in general, amplitudes, okay, let me say it this way. The way that symmetries act on shell is through ward identities, right? And these ward identities take the form of some symmetry, in our case Q, which will have to act on an amplitude AN with some states x1 through xn, and this will need to be 0. What do I mean by acting? I mean that you will have this Q dot, or let me say x1 Q acting on xi, xn equals 0, whereas sum over I equals 1 through n. Okay? And what do I mean by the Q action on a state is exactly what we had over there for the n equals 1 chiral multiplet, right? So let's look at what happens for the n equals 1 chiral multiplet, since we already have the action up there. So let's look at what happens to the 4-point amplitude, for example. So, right, the first thing to note actually is that in order for all of these to be physical amplitudes, right, it's necessary for this to actually have an odd number of fermions. Okay? If it's not clear to you, then think about it this way. So if you have an even number of fermions over here, once Q acts on this, it will necessarily only give you a sum of amplitudes with an odd number of fermions, right? So in order to have the word identity actually give you something useful, a relation between physical amplitudes, you're going to have to start with something with an odd number of fermions. Okay, so let's start with something with an odd number of fermions. Phi plus, phi minus, phi minus. We'll use the action above. We see that nothing happens to phi plus if I wrote the action correctly. Yeah. So actually, I shouldn't say phi plus because it's a scalar. It has 0 spin. But what I mean is phi and phi bar. Okay. Good. Good. So it doesn't act on phi plus, but it does act on psi plus. And it gives you an angle bracket of the momentum of psi plus, and it gives you phi. So A4 plus, phi minus, phi minus. Next state gives you 3, A4. Yeah, sorry, I should say that when Q goes through psi, it has to pick up a minus sign. So then phi plus, psi plus, phi minus, and then the fourth particle. Okay? Now, note that this is actually 2 equations because each of these is a 2-component object. Yeah? So in order to make this 1 equation, I can dot in with a particular, I can choose one of these to dot in with so that it becomes a relation between 2 amplitudes instead of 3. So let me choose 4. So this one will disappear when I dot in 4. And so I'm going to get, I'm going to get A4 for the all scalar amplitude to be related in this way from this identity after dotting in 4 to the amplitude with 2 fermions and 2 scalars. Okay? And I can play this game again, in which case I can relate this now, this 2 fermion, 2 scalar amplitude to the all fermion amplitude. Okay? Okay. So this should already give you a hint that what we should be doing when we're thinking about supersymmetry is not thinking about individual amplitudes, but thinking about groups of amplitudes that satisfy word identities in this way, right? So it doesn't make sense to say, does this 4 scalar amplitude satisfy supersymmetry? It makes sense to say, does this set of amplitudes satisfy supersymmetry? Okay, so this is where the superamplitude comes in. Okay? And this is the idea that I'm going to write down one object. So I don't have a different notation. Maybe I'll use curly A. And this capital phi notation. To mean a group of amplitudes, right? Which, and it's a 4-point amplitude between 2 positive chiral multiplets and 2 negative chiral multiplets. Okay? And I'm just going to write down a few things now, and then we'll go through exactly what all of these mean in a second. Okay? And implicitly over here, I've introduced a Grassmann parameter eta, which is how I define my chiral superfields. Yeah. Additionally, I can use this eta to define what I mean by the supercharges. Yeah, okay. So let's start with this. So what have I done? I've introduced a Grassmann parameter in a way that allows me to bookkeep all of my supersymmetry amplitudes, right? The way that I've done that is that I've introduced these superfields that contain all of the states in a supermultiplet. I have introduced these supercharges, and you can check that they will satisfy the algebra. So this is a true representation of the supercharges, like this is accurate. Yeah, good. So additionally, you can also see how I can pull out individual amplitudes from this superamplitude, right? The way that I do that is by noticing that, for example, the superfield, when I take eta to 0, gives me the scalar, right? So what that means is that if I take a superamplitude, phi plus, phi plus, phi minus, and I act on it with derivatives. So I should have said that the derivative will pull out psi plus, and just taking eta to 0 will pull out phi plus, right? So if I take the derivative on particle 3 and particle 4, and then I set eta 1 to 0 and eta 2 to 0, right? That is going to have to be equal to the component amplitude phi plus, phi minus, phi minus. Right? This is how you construct projection operators for your supermultiplet. Okay. Good. Okay. So, of course, this relies on what I mean by this object over here. So, what is this? As the name suggests, it's a delta function for Q dagger, right? So it's ensuring that Q dagger equals 0 in this expression. Okay. The form of the delta function, I'm not going to derive it, but I will give you the form of the delta function. Clearly, it has to be quadratic in eta because this is 2 equations that it needs to impose. Okay, 2 linear equations in eta that it needs to impose. So this is eta I, eta j, quadratic, ij, where I is less than j. Yeah. Okay. Good. Now you can check actually that this expression for Q annihilates this delta function. Okay. This should tell you 2 things. It tells you that this is a special amplitude because there is no polynomial in eta that is multiplying the delta function. In general, though, you could have in a superamplitude a polynomial of eta that multiplies this, right? It would, in this case, it would allow you to have amplitudes that have, for example, just 1 positive multiplet and 3 negative multiplets. Okay, so, good. So if you do have a polynomial in eta, the delta function in Q dagger makes sure that you're still Q dagger compliant. What it doesn't do is it doesn't guarantee that you are Q compliant, right? So whatever polynomial you multiply over here has to be annihilated by Q in order for it to be a supersymmetric amplitude of a supersymmetric theory. Okay, good. Now, when I have extended supersymmetry, it's easy to see that all I need to do is take Q, add an index, which is the same as saying take eta and add an index to eta, okay? Like this. And then my superfield becomes a little more complicated. So in the case of n equals 4 super Yang-Mills, I now have G plus, eta A, lambda A, eta B, phi AB, so the adjoint scalar, eta A, B, C, So this makes it even more clear what the representations are of these individual component fields in the superfield. Another thing that this tells you now is it tells you that if I want to, if I have some endpoint super Yang-Mills amplitude, then it's going to break up into sectors of powers of eta to some number, right? And this number is going to tell you whether you're MHV, NMHV, or what sector you're in, right? So actually, so yesterday, for example, what I said was an MHV amplitude is one that has 2 minuses and the rest pluses, right? Now, clearly, based on this, that's going to tell you that your super amplitude has a sector which is proportional to eta to the 8th, right? Because it has 2 negative helicity bonds. So this will come from, this comes from the eta to the 8th part of the super amplitude, AN, right? So similarly, as I keep increasing, it will come from the eta to the 2K part of AN. Okay, so now this already shows you at the level of the super amplitude that you can't have anything less than 2 negative helicity particles in this amplitude, right? Do you see why? It's basically because your super amplitude needs to have a delta function. But it needs to have a delta function for each of the supercharges, making this not quadratic, but octatic, eta to the 8th, right? So it has to have 8 etas in order for it to be non-zero. Now, there is one important exception to this, and luckily it's also something that will help us see how having a polynomial in eta has to be invariant under Q, okay? And that is the MHV bar amplitude in super Yang-Mills. Okay, so this is the plus plus minus amplitude in super Yang-Mills. Okay, good. So I should clarify that this delta function is, delta with n supercharges is simply a product of all of the deltas. Okay, good. Yeah. Well, this one? Yeah. So, yeah, I mean, yeah. So you have to be a bit careful about doing that only because these have, I mean, you can't just say that the delta function is not linear in Q because of the fact that this carries an index. So like Lance says, then you need to put 2 of the Q daggers together, giving you something that is quadratic, which then gives you the delta function. Yeah. Yeah. So, good. And, okay, yeah, sure. While we're here, so the action of Q dagger is multiplicative, right? Which is why it becomes easier to write down a delta function for it, because this is Grassmann stuff, so eta square is 0. It's a bit harder to write down a Q, but then you can just flip these descriptions and, yeah. So there's nothing special about Q versus Q dagger. That's a choice that I made. Okay. It's related to also the choice of saying what I'm calling MHV and what I'm calling MHV bar, etc. It's a bit arbitrary. Okay. Okay. So let's look at the counterexample that I said exists, and we'll see also exactly what part of it why it is a counterexample and why it doesn't fall under the purview of what I said so far. Okay. So, as I said, counterexample is going to come from the fact that this amplitude is actually non-zero, right? Now, this amplitude would have to be proportional, or it would have to come from a superamplitude, and it's going to have to come from eta to the fourth part, right? Because I have only one negative helicity gluon. Good. So I'm going to introduce this polynomial f, which takes the following form. 1, 2, 2, 3, 3, 1. Okay. Now, I just want to note that you have an A, some R index sitting on top of all of these etas. Yeah. Okay. So this polynomial is special because Q acting on it vanishes, and it's quite easy to see. So what does Q do? Q actually just takes away one of these and replaces it with a square bracket. Okay, so you get 1, 2, 3 plus cyclic, which is 0 because of the Schouten identity. Okay, I can't actually remember if Yaroslav introduced the Schouten identities, but it basically comes from the fact that these are two-component objects. You're adding 3 of them, and you have 3 of them, so there has to be some amount of linear dependence between these 3. Okay, good. So that's true because of Schouten. So meaning to say that actually this is true at all endpoint. Okay. Q dagger, on the other hand, acting on F, replaces this with an angle, right? So I have 1, 2, angle 3 plus 2, 3, angle 1 plus 3, 1, angle 2. Is that right? Oh, but it multiplies, right? So each of these comes. Eta 1, eta 3, eta eta 1, eta 3. This becomes eta 1 square, I believe. Yeah, and this becomes eta 1, eta 2. Yeah. Okay, so this goes to 0. You're left with this, and this vanishes. Did I make a mistake here? Yeah, this is 1. This is 1. This is also 1. Yeah. Good. Okay. So this vanishes because of three particle kinematics. Okay. So this is the part that's special in 3-point, that this polynomial is killed by Q dagger. So other than at 3-point where you don't have special kinematics, you have to have the amplitude be proportional to a delta function, and that's why all plus and all but 1 plus amplitudes have to vanish in a theory of supersymmetry because of the delta function. Okay. Good. Does anyone remember when I started? Okay. Okay, let me say a few more things at least. Okay. So one of the things I wanted to point out is that ward identities are actually, they've got nothing to do with tree-level amplitudes, right? So a nice example of how to use the ward identities to say something that's at loop level is to look at the following example. Okay, so say I wanted to calculate the all plus loop amplitude, okay, in non-supersymmetric Yang-Mills. So note actually that last time I told you that the reason that the gluon amplitudes vanish at tree level is because it's a consistent truncation. That is no longer true at loop level, okay? So this amplitude doesn't vanish at loop level for a non-supersymmetric Yang-Mills theory. Okay, good. So you know that this at loop level would come from a diagram that only has gluons running in the loop. Why? Because that's the only particle in n equals 0. Okay. For n equals 1, you could think of this as being having contributions from a fermion and from the gluons. Okay. And then finally, if you think about n equals 4, you now have contributions from the scalars. You remember that there are 3 complex scalars plus 4 fermions, plus then also the gluon contribution. Okay. This allows you to write the n equals 0 contribution, the n equals 0 1-point amplitude as the n equals 4, right? And then you want to remove the fermion box, so minus 4 n equals 1. And then what you're left with is the scalar, right? So plus scalar contribution. So this is what comes from the adjoint scalars in Yang-Mills, coupled to Yang-Mills. Okay, now the Ward identities tell you that for this helicity assignment, no matter whether you're at one loop or tree level, these have to go to 0. Giving you a convenient way that I think was first in Lance's paper with Zvi. Okay, maybe. So to calculate self-dual or whatever, all plus loop contributions for n equals 0 by just looking at a scalar box. Okay? Okay. So, good. Good. So we saw 2 examples, one at loop level and one at tree level, of how the supersymmetry Ward identities can be helpful to us. The final thing that I wanted to talk about will tie into what we spoke about last time, which was recursion relations, okay? So a natural question is, since we can recurse the component amplitudes of Yang-Mills, you can recurse the component amplitudes, the gluon amplitudes of super Yang-Mills, can you directly recurse the super amplitude, right? And this will require us to shift not only the brackets like we did last time. So I'll just remind you that the Bcfw shift that we looked at last time, if we choose I equals 1 and j equals 2, was this over here. 2 minus z, 1. Right? Yeah?
So obviously with the 4 matrix in the n equals to 4 super Yang is 4.0 amplitude, because if you look at the final equation, subtract 4 times k4, then we just call to one loop left, right?
Yeah, so that's what this is. That's what I want to calculate. Right? I want to calculate this object over here. Yeah, so I'm saying that this contribution equals this one, and then I'm subtracting out 4 times this one so that the fermion cancels. And then what's left is 3 minus 4, so minus 1. Sorry. Oh. Oh, this one. Does that make sense then? That cancels things, yeah. Oh, no. Okay, you understand the general principle of what's going on over here. I might have got the numbers wrong, but the point is basically that, okay, the point is basically that you have different particle contents in different supermultiplets, and you can use that to express a non-supersymmetric amplitude. And you know that the supersymmetric ones have to vanish, and so you can simplify the calculation you have to do, because obviously gluon integrands are harder to write down. They have internal polarization. Scalars are very simple. Scalar loops are well known and in 4 dimensions. Yeah.
If you want another superscript, then it's one matter or
chiral. Right. So here we're not talking about the n equals 1 super Yang. That's good. Yeah, thanks. Yeah, that's right. So this is the multiplet I had first introduced when we were talking about supersymmetry with just a scalar and a fermion. Gluons. That's true. Okay. I will give you the correct example next time. I just want to quickly talk about Bcfw before someone boots me. Okay. Good. So I just wanted to quickly introduce super Bcfw. Okay. And this involves shifting also your Grassmann variables in the following way. Okay. Now, once you do this, you have to also remember that your propagator is doesn't look like this anymore. Introducing a complete set of states requires you to do the following, where you actually integrate over the Grassmann variables, and then you have 2 superfields like this. So this is what inserting a complete set of states looks like when you have supersymmetry. Okay, so I'm just going to write down the super Bcfw formula then, and it should be pretty obvious that this is simply an extension of what we did yesterday, where you sum over the factorization channels. Now you have an integral, because this is the propagator. You have L, so left, 1 over p squared, right? Left and right are shifted amplitudes. Okay? And if you do this, and you do the analogous calculation of what we did yesterday for the Park-Taylor formula, you can find the super Park-Taylor formula, which is basically telling you what the MHV endpoint amplitude is, which is just a delta function. As we know, it has to be, because this has to be eta to the 8th, as we saw, for it to be MHV, followed by the usual Park-Taylor factor at the bottom. Okay? And the way to prove this, you have to do a little bit of Grassmann gymnastics, but it's basically the same as before, where you have one Bcfw term, and you have to use the fact that the n-1 point looks like this, and then it's a recursive argument, right? Okay. So maybe I should wrap up. I just quickly wanted to say that if you do the NMHV calculation, you get your each Bcfw term gives rise to what is called an R invariant, which has a lot of nice, interesting properties. So if you're interested, definitely try and do the NMHV calculation yesterday as well. There are a lot of new features of the calculation when you go beyond MHV. One of them being spurious poles, which have to cancel between Bcfw terms. Another one is the pole structure isn't as obvious when you just look at the answer when you do the NMHV calculation. So yeah, I definitely encourage you to go beyond MHV in your free time. But thanks.
Thank you.
Oh, thank you very much. I have 2 questions. First, could you also have, this relation between the scalar for n equal for the non-supersymmetric case to more legs, let's say? For example, if you have 6 gluon amplitude?
Sorry, if you have a 6 gluon amplitude?
Yeah, here in the left-hand side. Could you, is that applicable for?
Yeah, I mean, this I might have made a mistake in because I think I wrote it down wrong in my notes. But you can do a similar argument for endpoint amplitudes because the word identity is true for endpoint amplitudes.
And one more question is, this reminds me this famous Bern crossover replacement rule where you start with the scalar loop and then you do that for the gluon loop.
Yeah.
Is there any relation between these two?
That's basically this. I think they use the fact that you can do this supersymmetric decomposition to relate a gluon loop to the scalar loop. It's the same. It's the same. Yeah, that's where it comes from.
Okay, thank you. And that's also valid off-shell, I guess, right?
Yeah.
I have a question. It's not clear to me. When, for example, I look at the 3-point superamplitude, and I take the eta to the 4th component, how can I distinguish between having 2 helicity plus gluon and 1 helicity minus gluon, and having, for example, an helicity plus gluon and 2 scalars? It's still eta to the 4th. Right.
Good. So I was a bit sloppy when I said eta to the 4th because there's so eta to the 4th can mean many things because you have 2 indices now on your Grassmann variables, right? So you have the particle number and you have the R index. So eta to the 4th can mean eta 1, 1, eta 1, 2, eta 1, 3, eta 1, 4, which would make sure that the first particle is a negative helicity gluon, right? But if you want, for example, 2 scalars, then you would have something more like, for example, right? Where you're projecting out a different eta to the 4th part of your amplitude. So depending on which particle you want to be, which position you want to have what particle in, your component amplitude will be a different eta sector in this way. Yeah.
Okay, there are no more questions. Thanks, Shruti, again, and we have a break.